We're now going to talk about another application, geometric application of the theorems on intersecting families. Now this is about Borsuk's conjecture. And before stating the conjecture, I will describe the motivations of the conjecture. So the main motivation is this Borsuk-Ulam theorem in algebraic topology. So the Borsuk-Ulam theorem has many versions, and this is one of the versions. So imagine that you have an n-dimensional sphere which is covered by n plus 1 closed sets. Then one of these closed sets must contain a pair of antipodal points of the sphere. That's the theorem. So for instance, S0, zero-dimensional sphere, it's just 2 points, right? And if you cover this by one closed set, then you need to contain both of them. This is 1 and that's -1, that's fine. S1, right, circle, no matter how you try to cover by 2 closed sets, so one of the parts probably, I mean, this is not the general picture. Closed set could be the union of finitely many union of any small closed interval, but in this case, this is the one case, right? You have a pair of points. Okay, now this was a theorem in 1933, and then here's a conjecture by Borsuk in 1933. Is it true? Well, maybe I should say every set of finite diameter in Rn can be partitioned into n plus 1 sets of smaller diameter. Oh, what's the point? So the thing is, you can think of sphere, of n-1 dimensional sphere, as a set of points in Rn, right? And we know that no matter how I partition n-1 dimensional sphere by n sets, n closed set, there is a pair of points which are antipodal, and these pair of points have realized diameter. So no matter how I partition Sm plus 1 by n closed sets, one of them must contain a pair of points of distance 2. So you need to have n plus 1, right? So that's the motivations. All right. So in some sense, well, if the Borsuk's conjecture says n plus 1 closed set, then the lower bound is given by the sphere. But another example, but it's not closed set. I mean, we just say n plus 1 sets. Another example is think of the simplex. N-dimensional simplex, and if you partition it into n-1, no, if you partition it into n parts, right? So let's so this is two-dimensional simplex. You have 3 vertices, right? And no matter how I partition these things into 2 sets, 2 of them will be in the same set, and their distance is 1, right? A maximum. In n plus 1 n-dimensional simplex, we have n plus 1 vertices and a pair of them. I mean, no matter how I partition, you need to have you must have some part. No matter how I partition it into n parts, one of the parts contains a pair of vertices. So this number, if true, then n plus 1 is tight. Now let's define f of the n, right? So let f of n be the minimum integer such that in every set of finite diameter in Rn can be partitioned into f of n sets of smaller diameter. So we know that f of n is at least n plus 1. And the conjecture proved that f of n is exactly n plus 1. And this has been a conjecture for a long time. And the best known upper bound was Schramm in 88. He proved that f of n is at most something like some exponential function. So it's like 1.224 plus liter of 1 right? So this is far from the conjecture. The conjecture states that it's n plus 1, whereas this theorem only gives you an exponential upper bound. And there are known cases, for instance, so the conjecture is true if like dimension is 2 or 3, or the set is centrally symmetric. So if x is a point, then minus x is a point. And convex. So if x, y are points in the set, then any point in the straight line segments from x to y is also in the set. Or the set is convex with a smooth boundary. So in many of these cases, we already knew that this is true. Now, in 1993, Jeff Kahn and Kalai proved that the conjecture is false. They proved that fd, okay, let's now use d, is at least square 1.2 to the square root d for large d. I should say for all sufficiently large d. So not only the Borsuk's conjecture is true, but the bound, the lower bound, is far from being a polynomial. Right? This is not exponential function, but it's much faster than the polynomial, right? E to the square root of d is way faster than d to the million. Right, so let me tell you the proof. So first of all, we're going to consider the following construction of points from the set. Right? So let's say n is 4p minus 1 for a prime p, and choose n as big as possible, and yet n choose 2 is less than or equal to d, and let k to be 2p minus 1. Now if I have a subset of 1 up to n, I'm gonna map it to a vector in Rn, or actually you can think of it as vector in Rn choose 2, but n choose, yeah, it's not Rn, Rd, but n choose 2 is less than or equal to d, so I'm gonna map it into a vector in R to n choose 2. Let's say this way. So how do I map it? So ij coordinate, so I is less than j is less than, is 1 or 0. It's 1 if I is in A and j is not in A, and 0 otherwise. All right, now we may assume that phi A is actually a vector in Rd, right? Because n choose 2 is less than or equal to d, and you can pick all the remaining coordinate to be 0. So what is this length of this vector? If A has size k, then this is the number of pairs of I and j, where I is in k and j is outside k. So each vector has size exactly k times n minus k, and now we have a square root. Now let's consider for two sets A, B of size k and 1 up to n. We look at the distance between these two vectors. What's the distance? Distance is sum of the squares, right? So xij minus yij, sum of the squares of differences, right? So when is it counted? So if we said A of size k, B of size k, and you have intersections. Now the coordinates are different if these pairs have different value. Like for A, let's say this is 0, for B it's 1, or this is the other case. This coordinate was 1 for A, 0 for B. This is 1 for A, 0 for B, 1 for A, 0 for B, and nothing else. Right, so there are 4 possible things. So this is square root of right, so what's the size? So let me first count number of elements here. So it's n minus right, so n minus, okay, so n minus 2k minus a intersection b. So that's the size of number of people outside plus a intersection b. And then the complement of that is 2k minus twice A intersection B. Oh, yeah, I'm actually, it's, all right, n minus 2k minus plus twice A intersection B, and 2k minus twice A intersection B. So when is this maximized? So it's of the form n minus x, right? It's maximized when x is equal to n over 2, right? So distance between two points corresponding to two sets of size k is maximized when 2k minus A twice A intersection B is close to n over 2. This implies, but the thing is, n is, right? What is that? Just n is 2k plus 1, so 2k plus 1 over 2 is k plus half, right? So this means 2k minus twice A intersection B okay, so it's so it's k minus half. So A intersection B, and k is 2p minus 1, so this is 2p minus 3 over 2. So A intersection B is like p over, but wait, A intersection B cannot be, I mean, A intersection B is always an integer. So how is this possible? No, it's not possible. So the best thing, well, is minimized when A intersection B is as close as possible to this number. So it's going to be p minus 1. Right? So that's the construction. So we have the construction of set of points mapped from the sets of size k, and any 2 points have distance at most something, but the distance is maximized when the corresponding sets have intersection exactly p minus 1. All right, so that's the situation. So now what are we gonna do? We claim that any set of certain size, right? So let's construct the graph. Let GP be the graph on subsets of size k on of 1 up to n, such that A is adjacent to B, if and only if A intersection B has size exactly p minus 1. Now we're gonna consider the alpha of GP. So alpha of GP is the maximum size of an independent set of GP. So set is independent if no two vertices are adjacent. So that means it's, in other words, that's a maximum size of a set of K subsets of 1 up to n such that no two of them have intersection size equal to p minus 1. All right, and this is where we're going to use the Lumbar Suzuki theorem, right? Remember, K is 2p minus 1. We take L to be 0, 1 up to p minus 2, right? We apply along Babai Suzuki theorem. Then we deduce that alpha of GP is at most n choose p minus 1, right? So n is what? N is 4p minus 1, choose p minus 1. Now, why is this useful? Because we are trying to show that no matter how we try to partition it into certain number of sets, we must have a pair of points whose intersection has who has small. So let's see. So we are trying to show f of d, a lower bound. So f of d means I can, any set of points of finite diameter in Rd can be partitioned into f of d sets. Each of them has a strictly smaller diameter. But if you apply that to the points corresponding to these K subsets of n, then smaller diameter means that they don't realize a set of intersection size exactly p. So this has to be at least chromatic number of GP. Okay? This is because let me see. Chromatic number obtained from chromatic number of GP. Right. And chromatic number of GP is at most n, and most number of points, number of vertices, divided by alpha of GP. So this is 4p minus 1 choose k. K is 2p minus 1 divided by 4p minus 1 choose p minus 1. All right, so it's 2p over 4p, 4p choose 2p divided by p over 4p, 4p choose p. So it's twice, right, so 4p factorial over 2p factorial, 2p factorial divided by 4p factorial over p factorial, 3p factorial. So it's twice 3p factorial, p factorial divided by 2p factorial squared. Now we use a strings formula. So then this is at least twice 2 pi 3p and 3p to the 3p and p to the p divided by 2 pi 2 pi p and p to the p. And twice p, and 2 pi, that's squared. And some error term. And And if we cancel everything out, then what we get is square root 3 times 2 divided by 2, and 3 to the 3, and 2 divided by 4 squared, 16 to the p, and 1 plus all, yeah, right, so 3 to the 3, 3 to the 3, and 2 to the 2 squared, so it's 4 squared, 16. So what we end up is something like some constant times 27 over 16 p, and 1 plus the letter of 1. So again, some constant c times 27 over 16 n over 4, 1 plus the letter of 1. And what is 27 over 16? Right, so let me use calculator. Yeah, so this number is 1.13975 to the n. Now, we chose n so that n choose 2 is less than or equal to d, and n as big as possible. So this is bigger than d minus 1. So n minus 1 over 2 is bigger than d minus 1, which means that n squared over 2 is bigger than d. So this means n is bigger than twice square root of 2d. So the whole thing is equal to c times 1.39. Okay, if you don't like that, it's just 27 over 16 to the square root d 2 and square root d. And let me compute it. The calculator says this is 1.2032 to the square root d and 1 plus the letter of 1. And this is bigger than 1.2 to the square root d for all sufficient large d. All right. So that's the proof. So this shows that the chromatic number of this graph constructed from this subsets of size k is at least this 1.2 to the square root d. So those corresponding set of points in Rd cannot be partitioned into less than this number unless you have some pair of points of the same color, meaning the distance is still maximum. All right, so that's it.